Hello, everyone. NSBA and AISC are happy to bring you today's live webinar, Introduction to the FHWA Bridge Welding Reference Manual, presented by Ronnie Medlock of High Steel. Today's date is December 3rd, 2019. I am Nate Goner for AISC Continuing Education, and I will be the moderator for today's presentation. I would like to introduce today's speaker. Ronnie Medlock is the Vice President of Technical Services at High Steel Structures in Lancaster, Pennsylvania, where he is responsible for engineering and quality control and also plays a lead role in the implementation of technology in the shop. He has professional affiliations with the American Welding Society, the National Steel Bridge Alliance, the AASHTO NSBA Steel Bridge Collaboration, the American Railway Engineering and Maintenance of Way Association, and the Transportation Research Board. Prior to joining High Steel in 2006, he worked at the Texas Department of Transportation, where he served as Director of Technical Services at the Bridge Division, and before that, Director of Steel Bridge Fabrication Inspection for the Construction Division. Ronnie is a licensed professional engineer and a graduate of the University of Texas, Austin, with both a bachelor's and master's degrees in engineering. Ronnie, thank you for being here today, and I'll now turn the floor over to you.
Okay, thank you. So today we'll be talking about the manual. The manual runs to about 300 pages, so we won't go through great detail about it, but rather I'll provide everyone with some high-level overview of the manual and some key things that you may want to remember. I've got the URL of the manual there on the screen, and you can also find it by searching FHWA Bridge Welding or Bridge Welding Manual if you'd like to have that along. It is a free download of the manual. I'd like to begin by acknowledging a few key people that helped develop the manual. First of all, Justin Osell of FHWA. The idea of using the manual was Justin, as he initiated the project and also served as project manager for FHWA and coordinated with the reviewers and reviewed the content himself. I want to acknowledge Heather Gilmer and Dwayne Miller as co-authors, and in particular I want to acknowledge Heather's work. She made very significant contributions for making the manual as good as it is, and it really went the extra mile, and I appreciate that. I want to acknowledge Tony Ream of HDR. HDR had a contract with FHWA, and he was our liaison, official liaison with them, and also provided guidance and review along the way. And I also want to acknowledge the other reviewers, May Greco of Massachusetts DOT, Todd Neiman of Fickett, and Diane Wang, also of FHWA. So first, a couple of notes about welding. We all know welding today to be very important to steel bridges. Most of our steel bridges are comprised of two things, plate and weld, and also shapes for framing members. It wasn't always that way. Before we were welding, we were using rivets. Rivets were very effective. We built many bridges that way, but they were rather limiting in what you could do. You could only build what could be buttoned up with rivets, so to speak. And it was also a rather costly process, very labor intensive. When welding came along, it made steel bridges more cost effective, but also provided designers and owners with tremendous flexibility in what they can do, especially curved shapes and much larger girders and systems, as you see in these pictures. Also, if you consider these pictures as well, it was really welding of steel bridges that brought along the advent of direct connectors and long span grade separations. Welding is used in the shop, and then if you look on the right, also in the field. Welding gives us great flexibility for how we would fabricate and how we would assemble in the field as well. So welding made a very significant change to steel bridges of themselves, but also bridges in general. It really made us go longer and allowed us to do curves. And if you think about it, it fundamentally changed how bridges and even highways are made. So it was quite a revolution when welding came along. So why do we need a manual for welding? One way to think about it is to consider how times have changed in terms of bridge construction. If you go back to the beginning of the century, last century, you had the big mills that were kind of vertically integrated and did the whole thing. You had Bethlehem Steel that built bridges and also manufactured plate, U.S. Steel with American Bridge. Those companies were the primary builders of the signature spans, and they had the technology and knowledge to do that soup to nuts. But that's changed over time. We've gone from a few mills that do the big bridges to mills that provide material to a broad variety of bridge fabricators. So we've gone from the small group of people who are building to a rather large group of people over time. Also, there's been a change in the state departments of departments of transportation. I have 1917 down here as a highlight date. That was when we first started funding highway and bridge construction with federal dollars. That was when the cars came around. There was a recognition that we needed many more roads, many more bridges. So the federal government said, well, we'll need to spend money on this, and they wanted DOTs to work with to facilitate that construction. AASHTO was formed in 1914. Most of the DOTs started in the mid-teens, and then in February of 1917, the federal government started funding. From there, the construction really grew. The other thing that happened over time is we went from rivets to welds. Welding came in around the 1950s, and eventually rivets became obsolete. And the number of bridges that we constructed expanded greatly. This is just a characterization of the number of bridges that we build, and you stop and think about how many are constructed and who's involved. It's a very large group. So today we have the present situation where we have a great number of engineers who are responsible for welded bridge design and also welded bridge fabrication oversight. Some of those folks have got a lot of experience and knowledge, but not all do. And we need, FHWA recognize the need for guidance for all of those engineers who are out there to help establish better practices and provide them with the knowledge they needed to do the job. Hence the manual. So fundamentally, the manual does two things. It provides that knowledge for designers and also for material engineers, designers of steel bridges, and the materials engineers and their inspectors who have oversight over shop practices. Fundamentally, it also complements and sometimes explains the bridge welding code, D1.5. So as I talk through it, you'll see that a lot of what we have in the manual ties very closely with D1.5. Going through the table of contents, Chapter 1 is the introduction of the manual and talks about the importance of welding, applicable codes, etc. For each of the chapters, I have a brief snippet, not the entire table of contents, but each thing I show will give you a characterization of what's in that chapter. The second chapter goes into what is welding, the anatomy of a weld, amperage, wire feed speed, the terms that we use, variables, etc. But then we get into the bridge welding processes, the variety of processes that we use, like stick, submerged arc, gas metal arc welding, etc. Chapter 4, we talk about qualification of welding procedures, specification, and also qualification of welders. Chapter 5 addresses workmanship and quality, including hydrogen control, etc. Chapter 6 addresses inspection and quality control, what visual weld inspectors do, CWIs, the NDE that we use, etc. Then Chapter 7 specifically speaks to the fracture control plan, certainly an important part of welding. Chapter 8 talks about fabrication considerations for design of welded structures, kind of things in a practical nature that go on in the shop and what a fabricator needs. And then in Chapter 9, we go into constructability details. As a designer, if you want your design to be as cost-effective as possible, as fabricator-friendly as possible, what are the ways that you should do your details? What are the details you should use? Chapter 10 talks about the further engineered role in welded fabrication, talking about choosing codes, responsibility for shop drawings, how to handle nonconformances, etc. Chapter 11 is a catch-all of additional topics, other materials that could be welded, field welding, stud welding, and a look towards the future with the kind of things that are on the horizon, both in welding in general and also in bridge welding, in the bridge welding code. Chapter 12 is a list of resources. And then there are two appendices. One is Appendix A, which is a guide to reviewing and approving welding procedure specifications and PQRs, and I'll bring that up here in a bit, more detail, and then also differences between D1.1 and D1.5. So throughout the rest of my presentation, what I will be talking about are some examples of various parts of the chapters. Also, I will key in on those differences between D1.1 and D1.5. Finally, I will also talk about, in a little more detail, the approval of welding procedures. So talking about welds, the manual goes into the basic anatomy of a weld, and what is the base metal and the reinforcement of a weld, the weld metal, what is an effective throat, what are CJPs, PJPs, what are fillet welds, the kind of things you might expect to see with the guideline on welding. And also, we talk about the various welding processes. I want to go into a little more detail about arc welding and what that is. Most of the processes that we use in the shop are arc welding processes. We know that from what we think about the name, like submerged arc welding. But many of us don't stop and think about, well, what is it? What is it that's related to the arc, and why is that important? But if you think about making a weld, you know, depositing weld metal here and joining these base metals, the key is you've got to melt the base metal, and you've got to melt the weld metal. The only way to achieve fusion between the weld and the base metal is to locally melt and the base metal and the weld. Well, how are we going to do that? Well, the arc is key because the arc delivers the heat that we need to accomplish that. When we are growing up and we first learn about circuits, we learn that there's two key things about a circuit. If the circuit is closed, you have power, and if you open it, then you don't. That's pretty straightforward. What we don't talk a lot about is the arc, but that's also an important phenomenon, part of a circuit. If there is a small gap in the circuit, the electricity may jump across the gap. There has to be enough electric potential for the electricity to do that, but it will do that. The key thing about that jump is that creates what we know to be the arc, and the arc is very hot. Arc in a welding circuit is about 6,000 degrees, as an example. Well, steel melts at 2,800 degrees, so when we've used the arc for welding, we find a way to readily bring heat to the steel. So it's fundamental to most, although not all, but most of the welding processes we do. So with that ability to take advantage of the natural phenomenon of the arc and the heat that it can readily deliver locally, that allows us to weld. A basic arc welding diagram is as shown. You'll have a circuit, as I showed before. You'll have your base metal, and you'll have the circuit through the power supply onto the lead holding the electrode. The current flows through the electrode, might flow towards the steel or away, depending on the polarity you choose. And then the electricity jumps across the gap and creates this arc, hence the heat. So in an arc welding process, you'll always have a certain gap. The amount of that gap is very important for the nature of the weld that you get. You'll Because of that gap, you'll have the arc, you'll have the heat. The other thing that is important is the shield. The shield shields the arc and protects it from contaminants. If you get contaminants into the arc, then you'll get defects in the weld. That won't be effective. So that's basically all of the arc welding processes, and I'll talk about each one in a little more detail. This one is shown with a stick. This is shielded metal arc process. Most of the ones that we use in the shop actually have a coil feed. So that is the other thing that is fundamentally different between two of the processes and the arc welding processes we use. So the first one we'll talk a little bit about is shielded metal arc welding, or stick. This was the oldest process, the original process. You see the sticks. You see the welder holding the welding gun with the stick. The welder brings the stick to the work at the appointed gap. He'll drag the stick across the metal just to get a spark to get moving, and then holding the gap, weld metal will leave the rod and come to the weld. Here you also see there's a coating over the metal part of the rod. The coating is burned to create the shield. So you have your electrode and your arc, which is in here, and your shield. Shielded metal arc welding. Another popular type of welding is flux-cored arc welding. And flux-cored can be done either with shielding gas or self-shielded. Primarily, we use gas shielding when we use it in the shop. It's called flux-cored because you do have flux inside the consumable. The consumable helps with shielding and also can deliver particular characteristics of the flux that you might want for welding. You also see that there is gas that comes out. So the welding gun is hooked up to gas. It flows out to provide a shield. The electrode is fed from a coil, and you have your welding. So here are some examples of some coils you might use for flux-cored. You see the gas for shielding. You also get self-shielded flux-cored, and in this case there is no gas, but the flux itself is burnt and provides a shielding. We don't prefer that in the shop. We readily have gas, but sometimes it's useful if you're in a more remote situation or perhaps out in the field where you don't have gas and you want to just use the flux in the core of the electrode for shielding. That's the flux. The gas metal arc welding is very similar to flux-core, and you have the same kind of delivery, but you'll see there is no flux in the consumable. You see the gas that comes out to shield the arc. One of the key things with gas metal arc welding is the transfer mode. Depending on your electrical settings, there will be a certain mode of transfer when the droplets of weld leave the consumable. They may spray out. You might pulse spray them out. It could be globular or short-circuiting. These are designed to facilitate the type of welding that you do. Short-circuiting is a very low heat process intended for very thin materials. Consequently, it does not work for thick materials. The heat and a short-circuiting transfer is so low that it won't properly melt the base of metal to create that fusion. Excuse me. And so, therefore, we do not allow in the bridge welding code short-circuiting, but it is very useful for thin materials. These other transfer modes are allowed, and the more common are these top two. Another thing to note about this process and the ones we've discussed so far is that we call them open arc processes. In other words, if you see the welder welding as is shown here, you can see the arc. You don't want to look at it with your bare eyes. You'll damage your eyes. So welders always wear shields when they're using the open arc. Another variety of gas metal arc welding is gas metal arc welding with a metal core wire. In this particular case, you'll see that there is this a core, but in this case it's not a flux as a flux core, but actually other constituents. Those constituents will be used to help build the weld level more efficiently, or you might add alloy to change the characteristics of the weld. And then finally, we come to submerged arc welding. In this case, once again, you have a shield, but the shield is not a gas or something burned from the consumable, but rather powder that's delivered from a tube that comes down. So when you're welding with submerged arc welding, as you progress, the tube progresses with the welding gun, and flux drops out. You'll see a lot of flux here to make sure that there's good coverage. The flux that's not burnt up in welding is swept off and reused. So the welder progresses and delivers flux, and the welding is accomplished. Submerged arc welding is not an open arc process, so the nice thing about it for welders is that they don't have to have the same protection that they need for that open arc. Also, submerged arc welding lends itself readily to mechanization. Bridge fabricators like it due to that mechanization, and also because of the large consumables that you can use for submerged arc welding. For flux-cored and gas metal arc welding, a common wire diameter for those processes is 0.52 or 0.05 inches, not very wide. Whereas with submerged arc welding, the common diameters are 3/32 and 5/32. So much bigger wires, lots more weld metal. In bridge fabrication, we're building some big welds, so we really need a lot of weld metal. And so bridge fabricators and also fabricators of other structural elements typically find it very useful in the shop. So that would be in modern and current bridge fabrication, the real workhorse of bridge welding is submerged arc welding. But those other processes are certainly used as well. One other process that is used in bridge welding, although not very commonly, is electroslag welding. With electroslag welding, the weld is built in the vertical direction. These two are the base plates we're joining in this particular weld. You'll see that there's a copper shoe that's on the outside. It's cut away here, but it would cover the weld on both sides. The shoe has got water to keep it cool. So you basically build a cavity with your shoes and your plates, and then you feed in your electrode inside a guide tube that guides the electrode, and also some flux that sits on the top of the weld puddle. You use arc welding to first start the puddle, and then it reverts to resistance welding, and the puddle climbs this column. It'll climb that column at about 2 inches per minute, and it'll be a single pass weld for whatever is joined. So it's a very efficient process from the standpoint of welding, although it does take other equipment and setup in the shop. It is used a fair amount, but in bridge fabrication, but not a lot. So comparing the processes, the overview, stick was the oldest process, very versatile, rather low productivity, burning sticks at rather slow rate, but useful for out-of-position welding. In other words, welding overhead, welding vertical, also very handy in the field. Flux-cored and gas metal arc welding have similar characteristics, more productive than stick, not as productive as submerged arc welding. Fabricators use it for tack welds, small welds, robotic welding, and also possibly long mechanized welds. And when used with self-shielding, particular field welding. Submerged arc welding, very productive, very popular for long mechanized welds. Complete joint penetration welds. If you think about a bridge girder, we do lots of butt splices, flange and butt splices, which got a lot of weld metal. Those submerged arc welding is very popular for those. And then also electroslag welding. It's very productive in terms of each weld is only one pass. However, it's not currently allowed by the code for fracture critical welding or high performance steel, and that leads to part of the reason why it's not as popular in bridge shops as it could be. So let's talk about weld values. If you're responsible for welding, or you're concerned about welds, or you're going to use welds, what are the things that you're concerned with. What is important to you? Certainly you need strength. You want your weld to be strong enough to hold your components together. You're looking for ductility. You may be looking for weathering characteristics if you're in a weathering steel situation. You're certainly going to want enough toughness and material properties with, in terms of CVN. Also with geometry and fatigue detail. So toughness will be, there are two dynamics to toughness in weld metal. One of it is the weld metal itself, which is measured as a CVN of the weld metal, as the base metal is. And then also geometry, what are good fatigue details for your weld. You want soundness. You want your weld to be clean. You want your weld to be defect-free so that it will perform. And you're also interested in constructability. If you're designing a bridge and you're putting welds in your design, you want them to be something that the fabricator is able to actually execute in the shop floor. And also, even if it's not just a question of being able to execute it, being something that is the most cost-effective. Therefore, the ability to be made in economy. So generally, these, if you step back and look at your weld, these are the kind of things that you might care about in terms of a weld. And these are the things that are addressed throughout the manual. So let's talk about how you get there. First of all, let's talk about how do you get the strength and the toughness, and if you need it, the welding characteristics of your weld. The primary way that you ensure that you get these is by using the right code for your material. The American Welding Society has a family of 9 structural welding codes. So they're pretty much cover just about anything you use in structures. And as we know, there's one that is specific to bridges, the Bridge Welding Code. The other one to be mindful of is the Structural Welding Code. I mentioned at the beginning that I'll be comparing these two. The Bridge Welding Code is excellent for bridge welding, but that doesn't mean that it is necessarily the best code to use for every highway or transportation project related situation. And so that is the reason that I like to draw the comparison with D1.1. If you have something that you're welding that's a structure, and it's not in the Bridge Welding Code, and it's a steel, then you probably want to use the Structural Welding Code, D1.1. If you look in the various codes, you'll see that they align the base metal you intend to use with various weld combinations. So here I have a snip from D1.5. You go into paragraph 1.2.2, and it will tell you the materials that you're able to use with the code. Later in the code, in table 4.1, you'll see materials and associated electrode classifications. Here's submerged arc, shielded metal arc, submerged arc, flux-cored gas shielding, flux-cored self-shielding, etc., as we discussed. I didn't discuss electrode gas welding. That's one other option, not common, or to my knowledge, not used at all in bridge fabrication, but the code doesn't allow it. For each process, you're given classifications of electrodes that you can use under the Bridge Welding Code. Electroslag sends you to Annex I. So the intent of these combinations is to tell you that if you use this class of electrode with the material that you're using, and here I've got the table for A36, 50W, etc., and these tables go on for other pages, then you know, provided you follow the other provisions of the code, that you'll get the strength, the ductility, and the toughness you want out of your weld metal. This is how D1.5 works, and the other welding codes work in similar fashion. When you're choosing your welding code, you want to look in front at the approved base metals and make sure that it's there. The D1.5 2015 edition says follow any steel in A709. The 2020 edition no longer has this simplification of just 709, but does specifically list material grades, 50, 50W, 36, etc. And for each material that you find in Chapter 1 of the code, you'll find associated classification electrodes and for each process in the book. I emphasize that because where you want to be careful in terms of using the bridge welding code, if you have a bridge that is made of a material that's not in the code, and you specify the bridge welding code, then you've got a problem, because your contract says to go and do something that you cannot do. If it's not there, it's not there. In particular, as an example, there are no tubular materials as yet in D1.5. So if you specify D1.5 for tubular welds because you got some tubular material, then you're creating a contract that cannot be executed. So you've got to be very careful. And if you do have tubes, D1.1 is probably the right choice for you. Inside the bridge welding code and the other codes as well, you'll see standard joints. These joints are pre-qualified. They do not need to be tested. The fabricator can use them. You'll see that there are various aspects associated with each welding process in the joint. So, for example, this particular configuration, if a fabricator had a corner that he wanted to do with a single bevel, or a T that he wanted to do with a single bevel, he could choose this joint. Then he'd say, well, okay, which process do I want to use? And depending on which process, we would say, all right, what are my allowances for the root opening, root face, groove angle, etc. And then what are the tolerances? You'll see that there are as detailed and as fit up tolerances. So detailed means if a fabricator chooses this joint, let's say for submerged arc process, he can show F value, root face, of from 0 to -1/8 with a 1/4 inch max. So he could go as big as a 1/4, but no bigger, +0, and down to 1/8. That's as shown on the drawings. Then when on the shop floor, he's allowed another ±1/16. So you're allowed to move your required preparations by a bit in terms of how you decide to prepare them, show them on the drawings, and then is how you execute them on the shop floor. Also, you'll see that there are positions associated with each of these that are allowed. So, for example, with this joint, submerged arc can only be used in the flat position, but the other 3 processes may be used in all positions. This joint is standard if back gouged. Now, I emphasize that because if a fabricator says, you know, I can make this joint without back gouging, I don't need to, that's fine. The code says the fabricator can do that, but the fabricator has to qualify that joint. That joint becomes non-standard. So even if the fabricator wants to use the exact same configuration but only not back gouge, then the fabricator has to qualify that as a special joint. If the fabricator wants to change one of these settings, let's say, for example, doesn't want as big as a root face, the fabricator may say, well, I only need a 1/2 inch. So then the fabricator can do that, but he has to do a qualification. But to avoid that, the fabricator can simply use the details as shown in the code. The other thing that's required, and you notice in this particular joint, because you're in a T or corner situation, when you're in a T situation, you put a reinforcing fillet in that. This fillet weld refers to the one at the bottom, and this one, this side, refers to the one at the top, if you use a T. So let's talk about welding procedures and qualifications. An approved welding procedure is required for all welding under the bridge welding code. If you look in the code, you'll find that language. Most procedures, with the exception being stick under certain guidelines, require qualification testing. So the fabricator would have to decide what type of process and how he wants to go about it and what joint he wants to use, and then do qualification testing. So in the code, the procedure is known as a welding procedure specification, or WPS. Welding tests are documented on procedure qualification records. So the way that fabricators and others in the bridge fabrication industry tend to refer to these two documents are as WPSs and PQRs. And we'll say that the WPS has to be backed up by a PQR. Technically, that's saying that it has to be backed up by a record, and that's correct. We're emphasizing that, yeah, you have to do testing. We'll find that on the PQR that supports the WPS. I'll emphasize then, fabrication cannot begin until welding procedures have been approved. So that's an important aspect of support you might have to provide. If your responsibility is to approve the welding procedures on the job, then you'll need to get them back to the fabricator in time for fabrication to begin. So I'll talk a bit more detail about the qualification test. If you go in the code, you'll see this joint. You'll see that we prescribe a rather open groove that's welded from one side with typically a 1-inch plate. The design of this test plate with a very wide groove and a 1-inch plate is intended to provide a lot of deposited weld metal. To make a weld like this, and this is looking at it from the side, and this is looking in plan view, that's elevation, fabricator would have its first pass down here in one route, and then do another route, and then do another pass, and basically take anywhere from 8 to 10 to 30 to 35, depending on the process and the size of the consumable, passes to fill in that groove. Then the test specimens are taken, and you'll see that there's an all weld metal test taken right from the throat and Sharpies that test the throat. What you'll see in these specimens is that primarily what we're testing is the weld metal. These tests do a good job of providing a weld metal test. They don't necessarily reflect how that weld metal will combine with the joint to be used. The way the dilution that you get from a real joint would be different. The dilution being the amount of base metal into the joint. But the code sets up the test like this because the thinking behind the code is that we really want to be sure we have good good weld metal. We do conduct a tension test that tests right through the weld. But another important characteristic of weld metal is that it's based on those combinations that I showed you before. It's stronger than the base metal. So when you take a specimen of this plate out of this plate and you break it, you'll find that the base metal is always the thing that fails. So you get a very good representation of the base metal in the qualification of your procedure, and not necessarily exactly how the weld will work with those joints, but that has to do with why the code gives you standard joints. For fillet welds, if you have a single pass fillet weld, then you only have to do this test. If your fillet weld is multiple pass, under the current code, you have to do a groove weld test as well. But for single pass fillet welds, and most of the fillet welding we do is made in one pass only, you have only this test plate. So I mentioned earlier that there's a guide to approval of welding procedures. If you look in the code, it gets rather complicated. There are 4 different methods for doing your qualification tests. And then you write your welding procedure qualifications, your welding procedure specifications based on how you did your test. So if you're reviewing WPSs on a bridge job, you need to look at both the WPS and the PQR, and you need to understand how they interact, and you need to know what you're looking for. So we went through quite a bit of detail in terms of how the best practice for reviewing WPSs. There's a bit of an overview, talks about doing a high-level review to make sure you know what the fabricator intends to do with that procedure. Then there's a flow chart depending on the application and what type of welding he's doing. Tells you, how to continue to approve or reject if he's not satisfying code requirements. And then you go through the various review sections: fillet weld soundness, groove weld qualification, etc. So there's quite a bit of detail in there, about a 7-page document on how to go about checking WPSs and PQRs. Now, this is one of our first key differences between D1.1 and D1.5. Under D1.5, we have the qualification requirements that I described. But under D1.1, most welding procedure specifications are pre-qualified. I say most. There are parameters you have to be within in order to be pre-qualified. If you're not, then you do testing. But typically, the welding that we're doing in bridge fabrication and that most structural fabricators use, they are within the realm of what's pre-qualified under D1.1. So if you're looking at using D1.1 versus D1.5, you're not going to have qualification testing. However, you will have practice and associated requirements for welding procedures that will give you good, sound welds. That's the intent of how D1.1 is set up. It's intended so that if you specify it and the fabricator follows it, then you can be assured that you'll have the proper material properties in your weld metal under D1.1 without doing the qualification testing. So we talked about the weld metal properties. Now let's talk a little bit about soundness, making sure that we have a quality weld from the defect perspective. So here are some general categories of discontinuities that you might encounter in welding. Many of the discontinuities are related to welding technique. Incomplete fusion, if you don't tie the weld metal to the base metal, incomplete joint penetration, various types of cracks. These are the type of cracks that happen while the weld metal is cooling. So they're also known as hot cracks. And typically these have to do with either welding technique or how you set up the weld itself. There are other volumetric discontinuities such as slag, intrusions, undercut, overlap craters, etc. Profile, you have to have the right profile. And then things like spatter and arc strikes. This is an arc strike. The code does not allow arc strikes or spatter, and it speaks to the requirements for profiles and the allowances for other kind of discontinuities. So D1.5 addresses all of these, and these are all the kind of things that can happen during welding. There can also be problems with material, and D1.5 addresses those also. Laminations, laminar tearing that can impact your weld. And then finally, you have hydrogen-related problems, which can be porosity. Porosity can be from hydrogen. It can also be from other materials, so that it can be porosity. You see it up here in welding technique as well. And then also hydrogen cracks, which are known as cold cracks. So hydrogen is a particular concern in welding. A lot of the practices in D1.5 are directed towards controlling hydrogen. So we'll go into a little more detail about what happens and how you get hydrogen cracking. When you're welding, hydrogen dissolves into the weld metal, and it comes from a variety of sources. You want to try to minimize the hydrogen for good practice, but you can't eliminate it entirely. It comes from the atmosphere, which you're keeping out with your shielding. It comes from base metal. It's within the consumable. There's always going to be a certain amount present. And when the weld metal cools, the solubility of the hydrogen reduces, and as the weld metal solidifies, some hydrogen remains. Some of it continues to diffuse out of the weld metal, but much of it accumulates in the lattice of the microstructure. So if you get enough hydrogen in your lattice, and the weld metal, and there's enough stress on your joint, and you have a microstructure that is not strong enough to resist the stress given the hydrogen traps, you'll get a crack. So to get cracks from hydrogen, or what we call hydrogen-assisted cracking, you need to have the right combination of hydrogen, stress, and microstructure. But this is where the code helps you out, and steel welding practices help you out. The primary way to avoid a susceptible microstructure is to use the right material. Modern bridge steels are designed and established under D1.5 to be highly weldable, or to avoid a susceptible microstructure. This is also spoken of in terms of hardness. How hard is the microstructure? Historic steels can be much more questionable in terms of how hard they are, So some steels are very weldable, others are not. If you have an older steel and you don't know if it's weldable, you can use a carbon equivalency formula to tell you how hard is the steel and give you an idea of whether or not it's weldable. We call carbon equivalency another way of referring to the hardness of the material. The more carbon in your material, the harder it is and the more susceptible it is to cracking. So certainly, depending on your steel, you could readily get hydrogen cracking. But if you stick to A709 steels, if you stick with bridge welding code steels and the practices prescribed there, then you'll know you'll have a good microstructure. And stress, in terms of stress, that's hard to avoid. In a typical girder, we don't get a lot of residual stress in the types of welds that we build, and nothing that's going to overcome the strength of the weld leveling cracks. But sometimes we do encounter that in highly constrained situations. But for the most part, the constraint that you have in a joint is based on how it is set up. So there's not a lot you can typically do about that. The other thing we can control is hydrogen. Hydrogen can come from the consumable, as I mentioned, so we're very careful about how we handle the consumables. We keep coils in containers that are not exposed until we're ready to use them. We put stick electrodes into rod ovens to keep them warm, to keep the moisture off of them. We also use preheat. The code has preheat that is required based on the thickness of the material that you're welding to help drive hydrogen away. The thicker the material, the more preheat you need, because the thicker the plate, the more of a heat sink that will drive the heat, pull the heat away faster from the weld. So if you go thicker, you have to be hotter to make sure you have enough heat to keep the hydrogen out of the weld. If you need to, if the fabricator chooses, the fabricator can also add post-heat. The bridge welding code does not prescribe post-heat. It does prescribe preheat. It says if you use this amount of preheat, you shouldn't have a problem. But the fabricator runs into a situation where he has a problem. You may want to increase, you might want to increase the preheat, but you might want to add some post-heat. So all of these are practices you can use to avoid cracking, primarily the hydrogen control and the microstructure. And potentially, if you need to, you could even redesign joints to avoid some constraint. But under D1.5, you use the steels that are prescribed there and the practices that are prescribed, you won't have hydrogen-assisted cracking. We go into detail about in this mechanism in the manual in case you encounter it to help understand what you can do to avoid or solve a problem. So next in the manual, we talk about non-destructive evaluation. Non-destructive evaluation is a very useful tool for ensuring that you don't have defects. Magnetic particle is a method of checking for defects on the surface. You see the magnets here. The magnets are placed on either side of the weld. There's light here from the flashlight. Iron particles are sprayed. You see the technician who's spraying iron particles. They're dyed red, so you can see them. You get yellow ones as well. They spray down onto the weld, and if there's a discontinuity, such as a crack in the weld, that crack will break the magnetic field that's going through the surface of the steel through the magnets, or as brought in by the magnets. So the powder will accumulate at that crack or discontinuity, and it'll highlight it for you. So it's a good way to go looking for cracks on the surface. It's also, in this particular case, you see it being used on a final condition. Fabricators may also use it in process on welding if they're in a constraint situation and want to make sure that they've gotten everything out in the groove of a weld and make sure that it's clean. They might use magnetic particle as well. Another process we use is radiography or X-ray. So here you see the X-ray tube. X-ray can be conducted with an X-ray tube or with a radioactive source. You see the weld here. Film or a screen is placed underneath. The X-rays are shot through the weld to the screen, and if there's any issue in the weld, it'll show up. So for example, in this particular radiograph, you'll see that there was a line of lack of fusion in this particular weld. That's a very nice assurance of the welds that we produce. They're tested with either X-ray or UT or phase array, as I'll discuss in a moment, and that tells us that, hey, if a situation like this does occur, we'll find it, and we can make sure that we get that cleaned before the bridge is constructed. If something like this is discovered in a weld, the fabricator must fix it and then go back and test it again to make sure it's clean. Ultrasonic testing is another method. Here I just have a schematic. Here you see the plate surface, the weld metal, and transducers. The bridge welding code tells you that if you have a certain thickness of material, thinner material, you should use a 70-degree transducer and send sound to the weld. The technician who does the testing looks at an oscilloscope and observes the sound that bounces back from the other surfaces of the weld, and if a discontinuity is discovered, that will show up on the oscilloscope as a spike. And we'll say, oh, there's some problem in here. So by moving the transducer around, the technician can assess how much of a defect there is in the weld. If you have thicker material, then a 60-degree probe is used, and then for very thick material, a 45-degree probe is used. I've drawn them all here just to indicate them, but you would choose one or the other, primarily based on the thickness of the steel. The nice thing about this method versus RT is that with basic geometry, you can tell how deep your discontinuity is. In this particular weld, you can't look at it and tell how thick it is, although based on the penetrometer, you know it's a rather thin piece, it's a rather thin plate. This is actually a web. But just looking at this, you can't tell. And even how thick it is or how deep those discontinuities are. If this was a 3-inch plate and you saw that, you wouldn't know if you were near the surface or at the root or on the far side. With UT, you can tell. That's a very nice thing about UT. And typically if a fabricator does encounter this situation in a radiograph, before the fabricator fixes it, it'll go back and check the depth using UT. So newer technology coming into fabrication is phased array UT. And with phased array UT, instead of one sound path, multiple sound paths are sent, and they're sent at multiple angles. So at this one position, this amount of weld can be seen. So if you think about with a UT, in order to scan the entire weld with UT, you'd have to move this probe back and forth, and that's what technicians do. With phased array, in one position, you can get most of the weld. So in this particular weld, the fabricator might put a transducer here, scan, and then move the probe here and scan the rest of the weld. Under the code with phased array, you must establish a scanning plan that says, here's where I'm going to put my transducers to make sure that I've got coverage in the weld. So you see here in this view, the phased array probe is put on an index line. We have the weld here. The fabricator would decide where he wants to put the probe and then draw a line, say, all right, that's my index line. And then I'll run my transducer along the line. Okay, I show it out here in the middle to start at one end, go across. This string keeps track of where the transducer is as you scan. That's called encoding. D1.5 requires that when you do phased array UT, you use an encoder. You can do it without it, but by using an encoder, you get a permanent record of the entire scan of the weld. This happens to be a snapshot of a weld at one particular index point. This is the width of the weld, and this particular image is at this point on the weld. And you'll see at that point in the weld, we also are getting a spike on this particular view. Then if you look at this diagram, and this diagram is out of the code, it tells you how each of these views is oriented to the weld. So the C view is looking down on top of the weld. The B view is looking at it on this axis. The D is looking at it from the end. And then the A is not a particular orientation, but rather it measures the spike. So under the code, the allowance for pass-fail is based on whether or not you're beyond this gate. So here you see, this weld is, at this location does not pass. And actually, as you can see, this, all the way along the width of the weld, you see this defect. This happens to be the same joint that we saw in this previous picture with the RT, where you had a defect that goes the full length of the weld. So, but at this particular point, just to clarify, this is the sound that you see at that point. Yeah, this is not a very good weld, long defect, but it emphasizes the point. You can also use these views to help characterize, but the pass-fail of the joint is based on what's going, if you have something spiking out of this gate. So I put emphasis on this particular process because the community is in transition to phased array. Phased array came into D1.5 in the 2015 edition of the code. It's now in the code as an option. The engineer can choose to allow it. High Steel is doing testing. We've done some trial projects with the method. Florida, DOT did their own study and discovered that they got very good correlation between the code requirements of phased array UT and RT, and so now they allow it without engineer approval. Fabricator can simply choose to do it. And it really is better than RT, our workhorse method. First of all, it's better at detection of planar discontinuities. If you say you had something that was a very thin discontinuity like a crack, you might not see that with an RT, especially if that crack is in that same plane as the RT, for example, looking down on that weld. Whereas with phased array, because you're coming at it at an angle and at various angles, you're sure to catch that. So much better for planar discontinuities. It gives you that full volumetric view documentation, as you see. And I'll emphasize again, with RT, you can't tell the depth of discontinuity. With phased array, you can, as with UT. Also, RT is only useful for butt splices. Phased array and UT can also be used for T and corner joints, and phased array offers much better productivity. The results are available in the immediate as you scan. It's much safer. You don't have to worry about radiation in your shop or standoff. If you want to be safe with RT, well, you may have to either shoot at night or push workers away while you're working. You don't have to worry about that with RT. And also, the equipment is highly portable. You're not carrying a tube around and all the screen, etc. Just bringing the machine to the work. So it offers a lot of advantages. Our community is in transition to it. We're studying its use. It looks like, I'm hopeful, and I think many are, that within a number of years and not too far distant future, we'll be using all phased array or with no or very little RT. Another difference now that we're on NDE between D1.1 and D1.5 is that D1.5 mandates NDE, D1.1 does not. So if you choose to use D1.1 for your project and you want some NDE, then you need to mandate it. If you say fabricate per D1.5 as a bridge, you don't need to worry about specifying any NDE. It's already there. Now I want to talk about fracture critical welding. This is a chapter in our manual. In the chapter, we go through the history of fracture critical bridges, the Point Pleasant Bridge. We talk about this point, catastrophic failures due to welds, and a key point being that there has not been a catastrophic failure of a bridge due to a weld that satisfied D1.5. So that's a very good track record and should give all of us confidence. We talk about proper use and abuse of fracture critical. Fracture critical is only intended for tension, not really intended for pedestrian bridges. We talk about designations, and we also talk about detailing. One of the key things that we recognize in developing the manual is that there are no standard practices for how to show what is fracture critical on a bridge project. It's always done. The designer is responsible for telling the fabricator and others what is fracture critical. And in fact, designers do that, but they do it in a variety of ways and not always effectively. So in the manual, under the fracture critical chapter, we have some recommendations for how to show what is fracture critical. And what we say is that what you should do is on your element, use a sketch to show where you are or are not fracture critical. The fabricator needs to know so that the fabricator can properly order materials. This flange and this flange must be fracture critical material, but this one does not need to be. When you look out on this web, you may think, well, the fabricator is probably going to just use one plate, so why does the fabricator care? Well, the weld up here is going to be fracture critical, but not necessarily down here. And also, if there's a weld that's going across the plate, it would not necessarily, down here, it wouldn't need to be fracture critical procedure. Now, if a fabricator was welding across that area, the fabricator would use the same procedure, just logically. But if there were a repair or something else that was an issue in the material in this area where we're not fracture critical, then the requirements are different. So you really need key details on what is and what is not fracture critical. Also, designers should tell fabricators what attachments are fracture critical, and if they're not. The code, LRFD, tells you that if you have an attachment to a fracture critical member parallel to the direction of stress, then that component also needs to be fracture critical. Fabricators cannot really necessarily assume whether or not an attachment is fracture critical. They can guess pretty well. If it's stiffener in this situation, it's probably not. But we might guess wrong. So inevitably, fabricators will issue RFIs to ask, is the attachment fracture critical or not? Far better to go ahead up front and make that very clear. However, fabricators do not need to know whether a weld is fracture critical. If you're welding a fracture critical component, then it must be welded using a welding procedure that's fracture critical. So given the knowledge of where the FC zones are and which elements are fracture critical, the fabricator can properly know whether or not welding is to be done with a fracture critical procedure. So if the best practice for showing what's fracture critical is to use sketches to show the limits, to be clear about the attachments, but don't designate the welds. So there's another key difference between D1.1 and D1.5. D1.5 addresses fracture critical welding, including increased preheats, expiry of procedure qualification, and increase in NDE. Of course, D1.1 is silent about fracture critical. We also talk about intersecting welds in D1 in the new welding manual. FHWA has got another task specific to intersecting welds underway. So I mentioned that we intend synergy with the publication that is coming from that task. That is a much longer task about intersecting welds in the problem, but we do touch on it in the manual. The concern about intersecting welds came from the home bridge, and actually there is some guidance that was intended for the home bridge that got misconstrued. The home bridge, as you may be aware, is a bridge that had a significant crack. I was taking a look at the detail that cracked, and this is just a simplified representation of it. The bridge had this condition, and you'll see it here, and I show you. You have your transverse stiffeners, and you have these plates that were, these gussets that intended to attach the framing. So the gussets came around the transverse stiffeners. This resulted in a situation where you had constraint in this area on the web from the weld that attached the gusset and also this stiffener. There's also a very small gap here, which meant that there was no relief from the constraint in the web here. In some cases, these welds, based on tolerances, were even touching. But even with a gap, there was little to no restraint. Further, there was a discontinuity in the fact that you had a discontinuous weld, which gave you a crack-like condition. And then you also had tension down here. So on a very cold day, under this tension, one day the bridge cracked. So the FHWA did an investigation of the situation and provided some guidance based on the investigation. And one of the things they said that to help avoid the condition that resulted in the hone was, well, be mindful of where welds are intersecting. That got misconstrued over time to where, well, welds shouldn't intersect, and then we won't have this problem. Well, that was an extrapolation and not intended. So now, many times people are very concerned and afraid of welds that are intersecting or afraid of welds that are touching, and they don't need to be. But it had its roots here and just getting misconstrued on that recommendation. This is a high-level description of that. The manual goes into it. The FHWA will have better guidance coming out in about another year. It goes into great detail. Because you do need to, in certain situations, be careful. But that does not mean that welds should never touch. We often have intersections in fabrication. So if you look at this particular bridge as an example, you'll see we always have flange butt splices and web butt splices, and then welds that join the flanges to the web. So welds that touch in a girder are very, very common and no problem. Sometimes you'll see an offset, as is used in this particular bridge, but that's not necessary. You could, if you wanted to, you could align the welds in design. Offset is fine as well. But certainly there's no problem with these welds touching. Now, on the other hand, if you were joining built-up sections, so as I showed you in an early picture of that field welding, if you were joining girders that were complete and you had a full pen weld in this web and then in these flanges, you would say, oh, I need to be careful about how I connect down in this corner. So I would want to use an access hole to avoid that intersection, because you could have a quality problem here. So there's situations where you want to be careful. But saying that, welds shouldn't touch is simply not necessary. So the manual then goes into constructability in terms of arranging your welds and how you go about it, what are the best practices. And so, for example, if you're building a box, this is a box that was shown in that early slide that was an arch bridge. This particular box was designed like this. Fillet welds on the outside and no other welding on the inside. Also not full penetration welds. This is highly constructible. If you have a weld on the inside, then that weld has got to be made when the box is closed. That becomes a challenge. If you can weld on the outside only, that's better. And if it's a fillet weld, that's the best constructability because there's no prep, and usually that's only one pass. These configurations also show outside welding only, but they're full pen welds. And so, you see a detail here. You do have to use multiple passes and a bevel. So this one helps by avoiding welding inside, but is not as constructible as this one. So the manual has details like that. We talk about skewed joints. We often see skewed connection plates, especially on highly skewed bridges. We have recommendations on how to handle that skew. Up to a certain point, you can expect a fillet weld, but afterwards, down here at 60 degrees, you should probably go to a PJP. We talk about trade-offs between CJPs, PJPs, and fillet welds. We talk about situations that are challenging. For example, multiple bearing stiffeners. If you attach a bearing stiffener in one location, you have to use a lot of fuss to make sure you have contact. Then when you attach your second bearing stiffener, sometimes this will open up, so you have to come back and remediate that. Then when you've got them both ready and you come back with the third, you might then introduce a gap at the first ones. So we go into detail about why you want to avoid this. And in this particular situation, if you have jacking stiffeners near bearing stiffener, we recommend you use a partial depth jacking stiffener. We have access constructability. If you have two elements that are close to each other, you need to think about the welder being able to get in between there to weld. And what we say is that take the height of your element and add 3 inches, and that should be plenty of room. We talked about how much room a welder needs. to be able to reach inside the closed configuration, or if the welder needs to get inside a box to do welding. And think about the welder, the amount of heat that's in there and comfort in trying to do that weld. So they have constructability guidance related to access. Through the manual, we talk about how to do flange transitions. Most people are well aware that if you have different thicknesses, you should show them to the outside, not show them to the inside. Although, if you have some rather long spans and you want to have thicknesses to the inside, you can do that readily if you make them only at field splices. So you see here a field splice and a thicker flange at this location, but no transition. So each individual girder has the same depth. So that's okay. And in fact, this was used on the Tappan Zee bridge replacement very effectively, which they intended because they wanted a flatter top surface for deck panels. We talk about a preference for if you're using thickness transitions to avoid width transitions. It requires more material and it doesn't allow the splicing of parent plates, which is preferred. Also, to facilitate splicing parents, if you can, keep your girders and splices similar across the width of the span. So a lot of different recommendations like this. Here's a picture that emphasizes why you want one line on your girder. And most fabricators have equipment that will do this weld in one pass. If you have a thickness transition out here, well, fabricator won't be able to use this equipment. Fabricator could do it, but it won't be constructible based on the equipment that most fabricators have. We talk about symbols. We emphasize that you want to follow AWS 2.4. That is a very good resource to have. It looks like this. One of the things that it's worth emphasizing, though, if you have a very odd configuration, you're not sure how to do a symbol, don't be afraid to use a sketch just to make sure that what you really intend is clear. We talk about field welding. On to other topics. Here's a case where fielding was very effectively used to retrofit on a bridge. And this particular bridge, field welding was used to give a very clean structure. The designer didn't want a bolted splice. It's a highly aesthetic bridge, and so he used field welding. So it's the kind of thing you may want to think about. Field welding is a good process. You want to be careful and make sure you use good controls, but if you follow D1.5, you'll be fine. We talk about in the manual aluminum and stainless, reinforcing steel, and also welding coated members. Further to D1.1 and D1.5, D1.1 has a greater range of materials and also tubular materials and joints. We have a section on resources, resources for your library. Here's the first page out of it. You'll recognize some of these. It goes on, and there's a lot of good references that you can use for your welding. I'd like to emphasize this one. This is an AISC primer that is on welded connections. Dwayne Miller is a primary author, the author of this document. Just recently was updated. Design Guide 21, you can purchase this from AISC. He goes into much greater detail on structural welding. Much of the work that we have in our manual is similar, or we even excerpted from this manual as we felt we needed it. So if you look at it, you'll see some synergy, but again, you'll see much more detail. So it's a good resource. Then we have a section on things that are out there in the future. For example, full matrix capture, total focus method, phase array. I talked to you about phase array. This is what a scan of this aluminum block looks like with phase array. Using total focus method, this is what it looks like. So this is an enhanced method, a phase array. Phase array is already an enhanced method of UT. But enhance it further, a lot more data, you can get even a better image. So maybe something like this will come into practice. Also, details that may be handy. So, for example, this pipe stiffener. This is a way to attach a connection plate at a highly skewed joint that you may want to consider. There's several other topics that we talk about: 50 CR, material, tubular structures, again, which is coming into D1.5, etc. Laser welding, multi-wire gas metal art, quench and self-tempered grades, castings, etc. And then also this homopolar welding. I'm about to show you a video, and I'll turn it back over, Nate, for that. With homopolar welding, homopolar welding has all welding at one time. So let's go ahead and see that video. We'll just take a couple of moments. All right, so what happened there was when you saw that flash, the entire section of what we were welding happened at one time. With homopolar welding, the section you're welding, no matter how thick it is, whether like this plate, it was 1 inch by 6 inches, or whether it's a typical flange that is as big as 2 inches by 24 inches or even bigger, can be welded in that same space of time. The way it works is that you use a homopolar generator to build up a big charge, and you also put a lot of pressure on the joint. You put 20 KSI pressure, so that's a lot of pressure. You hold that pressure on the steel, you introduce that charge, and the charge locally heats the surface, and then bam, steel goes together. Let's look at that one more time. All right, so here is where the charge has been built up. It's about ready to go, and then it'll fire the machine. Remember, it's a 1 inch by 6 inch opening. That was a weld. Really cool. Now, the equipment to generate that amount of pressure and that amount of heat is, pretty significant, maybe in the millions. So I don't know if we'll see it in the shop soon, or who knows when in the future. But it's a kind of thing that is really way out there on the horizon. I thought I'd share with you as we draw to a close. So finally, I want to emphasize that to find the manual, you go online to the Federal Highway website, very easy to find. You'll see a series of manuals there. You'll see the bridge welding manual. Just wrapping up, remember that it's free online. You can find it. Some key things that we talked about: use D1.1 when not, consider using D1.1 when D1.5 is not appropriate. Be sure to expedite your review and approval of welding procedures. Consider use of phase array in lieu of RT. Clearly identify fracture critical zones and attachments, but don't call out the welds. Don't be afraid of touching welds. Consider use of field welding to facilitate new construction as well as retrofits, and follow the manual constructability recommendations for the best practices, and also check with your local fabricators. The best practices are often based on their preferences and their equipment. It's a good idea to be in touch with that. Finally, I'll add I welcome your feedback. This manual is complete and published, but there may be opportunity in the future to provide an update. And if there are other things that folks need to know, let me know. Perhaps we can get them published. Thank you.
All right. Thank you very much, Ronnie. So we have some time here in the time that remains to go over some questions that came in from the audience. First, as we usually do with webinars here at AISC, we're going to go ahead and do a couple polling questions to test the audience before we get to those audience questions. So let's go to those questions now. And here's the first polling question. This is a true-false statement. So it is as follows: true or false? Under AWS D1.5, welding cannot proceed unless welding procedures have been approved. And again, the audience can participate by simply selecting the answer they think is correct on their computer screens. Again, true or false? Under AWS D1.5, welding cannot proceed unless welding procedures have been approved. Okay, answers are slowing down, so let's go ahead and look at those results, Ronnie. And it looks like the response is overwhelming that that is a true statement. Did they get that correct?
Yes, the code requires that all welding be performed in accordance with an approved welding procedure. So that is the correct answer.
All right, good job, everyone. Let's see if the next one is any more challenging. And here's the next question. Which of the following is not a reason that phased array ultrasonic testing is a better method than radiographic testing for inspecting CJP welds? Is it A, that phased array UT testing has a longer history of use in bridges? B, that it is better at finding planar defects? C, that it is safer? D, that it is more productive? Again, which of the following is not a reason that phased array UT testing is a better method than radiographic testing for inspecting CJP welds? Like most of the results are in, let's go ahead and see what everyone thinks. So Ronnie, it looks like about 90% of the audience thinks that the correct answer is A, a longer history of use in bridges. Did they get that one correct?
That is correct. Phased array is better than RT, but it's new. So it's not better because it has a longer history. However, those other reasons are good reasons of why phased array is a better method than RT.
All right. Good job, everyone. So let's go ahead and move to some of the questions that came in from you all during Ronnie's presentation. First one will bring us back to, we'll go back to slide 30 in this discussion on the AWS codes. And the first question was, what AWS code should be used for a situation where you have A709 grade 50 CR steel?
Yeah, that's a very good question. I'm glad that question was asked. You know, 50 CR has been used on bridges, and so you'd say, well, that's a good bridge material. But D1.5 does not address 50 CR. So what would you do? There is a method in of welding stainless steels in D1.6. D1.6 is the AWS code for welding stainless steel. So the best approach for welding 50 CR is to use a hybrid of D1.6 for the welding procedures and D1.5 for the other bridge welding requirements. Yeah, so it's not a very clean solution. It's not possible to simply say, oh, use this code and walk away like you can with bridge steel. So when you're innovating and using something in a bridge for the first time, you have to be a little creative. However, it is very, very doable. You'll just simply need to have a special specification that says, okay, I want to follow D1.5 for these requirements. For example, for the butt splice testing, for the requirements for welding procedure qualification, except when you qualify, you're going to use this material, and you're going to use consumables that follow D1.6. So what you have to do is you have to page through and think through the various requirements that apply to the shop floor and come up with a special specification. So right now that's true of 50 CR. And any time you're using a material that is for a bridge that's innovative. However, I will note that the Bridge Welding Code Committee is adding 50 CR to the code. And so that is underway. And that didn't make won't be in the 2020 edition, which comes out next year, but that will be available in the next edition. Good question.
All right. Let's stay in this area of the presentation. And the next question is, can older steels such as A7 that do not require chemistry control be welded? If so, what should be considered during the plan and specification development to ensure weldability?
That's a very good question. The question is maybe. You know, A7 did not have chemistry controls, as the question stated. That doesn't necessarily mean it couldn't be welded. It may or may not be. If possible, the best thing to do is, during project development, do some chemistry testing of the material that you've got. I mentioned during the presentation that you can check the hardness of your steel and therefore its weldability, basically, with using a carbon equivalency formula. D1.5 has a pair of formula inside, and then there are others that you can find readily through various guidance, and they're very similar. So what you can do is do some chemistry testing, find out what constituents you have, and then use those formulas to discover whether or not your material is too hard. Some very older steels also had sometimes had other constituents that were unusual, such as phosphorus, which could make things very difficult to weld. So if you could look in your manual, you'll find some more guidance about that. But if possible, up front, do your testing, and then you'll know where you're at. Another approach could be to, in your contract, specify that weldability will be established. But I think you're probably better off, if possible, to know that going into the project than discovering it later. You know, if you say you have a material and you say weld it if possible, and then it's not, you're really in a jam. So that would be my recommendation.
All right. Moving forward to slide 41, and the question is, you mentioned that there were some various sources of hydrogen that might cause these cracking mechanisms. The question is how would one know whether electrode is low hydrogen or not?
I told you that and maybe what you can do is go to that slide that shows the consumables, Nate. I told you the code prescribes certain consumables. That's where, we have that table that shows the material and the consumable. When you look at those electrode classifications, those classifications align with an AWS A5 specification. And those specifications specify that the consumable is to be provided to those requirements. Thank you, that's what we're looking at. One of the characteristics of these consumables is that they are intended for, I'm going to say, low hydrogen, in quotes, situations. I say that in quotes because we talk about low hydrogen as a practice, and we use that term in our codes, but there isn't an official designator that says at this level of hydrogen you're low, and above that you no longer are. Now there are some low hydrogen designators for stick electrodes, but for most electrodes you won't get a low hydrogen designator. So the best practice is to simply use these classifications under D1.5. And more simply, if you're in a situation where you're concerned, say fabricate and weld to D1.5, and then you don't have to be concerned about either the consumable chosen or the practices used in association with those consumables.
All right, and we're a little bit getting past time. Let's just do one more question. Looking at slide 61, and the question is do you know when will tubular steel be added to D1.5?
That's a good question too. Yeah, our next publication date following 2020 is most likely 2025. So that's one possibility. We've also talked about the possibility of doing an interim edition of D1.5, there are two sort of big ticket items that are underway. One being the 50 CR that we talked about, and the other being the tubular steel. Once those are complete, we may decide, oh, you know what, let's go ahead and publish a special edition of the code. The status of the tubular ballot is that it's been once through subcommittee, it'll go back through that. The goal is to have the tubular provisions to AASHTO for their 2021 meeting. If we make that goal and it passes, we could possibly issue a 2022 edition. Now, another thing to remember, once provisions do pass AASHTO, those are published in AASHTO interims. So often that's another choice to look at, well, here's something that's not in the code, but we know that it has been approved by the committee. So the goal is to be through voting through in 2021, and then possibly we'll publish an edition in 2022, but the AASHTO interims would also be available.
All right. Well, thank you very much, Ronnie, for those responses. And just want to let folks know, if you submitted a question that we didn't get to, we didn't have quite time to get to all the questions that came in, we will work with Ronnie in the coming week to respond to those unanswered questions via email.